Welcome back. In this lesson, we're going to be looking at the syllabus point A1.1.8 Describe the concept of compression. So far, we've looked at the hardware side of things, and we know that there is something called secondary storage, and we need to store data on it. But storage is never unlimited. There's always going to be a device at the end, and the device is always going to have a limit. Therefore, we need to make sure that the data is compressed, not just for storage purposes, but also for transmission purposes. Now imagine when you want to watch a movie, you actually get terabytes of data. That will take so long that you won't be able to enjoy the movie. You will have to wait for the movie to be downloaded first before you could view it. And that used to be the case for compression. Nowadays, with advanced algorithms, we can take gigabytes and terabytes of data and we can ensure that it's compressed to such a high degree that you can enjoy a movie while it's being downloaded. So let's look at what compression actually is. Compression is the process of reducing the size of digital data so it takes up less space or transmits faster. It is essential in applications such as image storage, video streaming, file archiving, and data transmission over networks. And there are two main types of compression, lossy and lossless. Let's look at lossless compression. Now, lossless compression reduces the file size without losing any information. The word lossless means that you are not losing anything. The original data can then be perfectly reconstructed after decompression. So it preserves the original data exactly and it's used where accuracy is essential, such as when we want to transmit text files or code. You don't want to lose pieces of writing or code because that can lead to errors. A typical example of lossless compression that's asked about in the exam is run length encoding, or RLE for short. RLE is a simple lossless technique that compresses whatever needs to be compressed through statistical redundancy. And what exactly is statistical redundancy? It's the repetition of information within a dataset that does not contribute to its uniqueness. For example, you might have a bunch of pixels and they all are the same color. You can group them together. We can then store the value and the number of repetitions like 7 black, 6 green pixels, and so on. It is best suited to data with lots of repetition. So simple images, especially black and white images, icons, text, that's where this comes into play. On screen, you see an example of some text data. You've got some A's, some B's, and some C's. And if we say that each character takes 1 byte of storage, it will take 11 bytes to store the original data. Now we can see that A is being repeated. So instead of writing all of those A's, we can simply write 6A, 3B, 2C. Now we're just going to simply have 6 characters, therefore 6 bytes. We saved ourselves 5 bytes. And that's basically the essence of run length encoding compression. It is effective for data like bitmap images with long runs of the same color, but it's less useful for complex or noisy data where each pixel might be of a different color. And it's lossless because when you decompress it, you already know that the 6, the number before the letter, is the amount of repetitions of that particular data. So everything can be restored. The original file is completely restored. Okay, let's move on to the second type of compression, lossy compression. This removes some data permanently to achieve high compression ratios. The decompressed file is not identical to the original, but is often visually or audibly acceptable. So it's very useful for reducing media files where minor losses in quality are acceptable, especially if it reduces bandwidth or storage, but the quality difference is not perceptible to us. An example of this is transform coding. Now this is the example you need to remember for the exam. So data is transformed into a frequency domain. For example, we use discrete cosine transform, DCT, where less important frequencies are discarded. So images, for example, are broken into sub-images and data is taken from the spatial domain, which is basically the pixel values, as pixels take up space, obviously, in an image. From that spatial domain, we break it down to the frequency domain. So the output breaks the sub-image into low and high frequency coefficients. The high frequency parts are then compressed where some detail is lost but not enough to make a difference in quality. And at this stage, RLE can be used along with other algorithms like Huffman and zigzag scan and so forth. Now, transform coding is used in formats like JPEG for images, MP3 for audio, and MPEG for video. It removes imperceptible data and it is what allows Netflix, YouTube, or Spotify to stream efficiently. Now, just like the other ones, you need to be aware of scenarios and you need to justify which method is suitable and why. So on screen, you see a few use cases and preferred methods and trade-offs. So let's look at text files and source code. For that, lossless is preferred because no data can be lost. For photographs for websites, we use the lossy compression method because small size is more important than perfect fidelity or quality. For medical images or legal records, we'd use lossless because data integrity is critical in these situations. For streaming video or audio, lossy method is preferred because fast transfer and playback are prioritized. So when we talk about trade-offs, it's what we're giving away for the sake of compression. For example, for lossless, we're trading quality for size or transmission speed. And for lossy, we're trading speed and small storage sizes for quality. Now on screen, you will see a series of key terms related to this particular section. Please do pause the video and go through them. Make sure they are in your glossary. These are really important, and as usual, these could be 1 or 2 marks in the exam. Now, hopefully you know enough to answer the following practice questions. You should be able to explain the difference between lossy and lossless compression. You should also be able to give examples where lossless compression is essential and why. You should be able to describe how run length encoding works. You should also be able to explain the role of transform coding in lossy compression. And you should also be able to justify why lossy compression is used for streaming video or audio. That's all for this particular lesson. If you do have any questions, as usual, get back to me in the comments, and I'll see you in the next one.